In this section of the MECH study group, we will be covering the topic of maintaining heating, ventilation, air conditioning, and refrigeration systems. Approximately 11% of the questions asked on the MECH exam will be on the area of maintaining heating, ventilation, air conditioning, and refrigeration systems, which means that about 11 of the 100 questions will be about the concepts of monitoring and adjusting pneumatic systems, performing scheduled maintenance, and repairing and replacing HVAC components. We are going to be covering the following tasks that come directly out of the MECH Test Preparation Manual: how to use a SLING psychrometer, how to use a gauge manifold set, the various components of an air conditioning system, the difference between refrigerants, basic troubleshooting of HVAC systems, how to troubleshoot and calibrate the pneumatic control systems, various ducting and damper systems, the types of pneumatic valves and how they operate, how to calculate airflow, how to measure static pressure, understanding hydronic systems, and how to read the symbols for HVAC components on blueprints. The first area of knowledge to understand is how to use a SLING psychrometer. A psychrometer is a device used to measure humidity. It consists of a dry bulb thermometer and a wet bulb thermometer. Their difference indicates the dryness of the surrounding air. First, remove the cap from the psychrometer. Dip the wick into water to saturate it. Fill the psychrometer reservoir with water. Replace the cap. Examine the wick to make sure it's covering the wet portion of the psychrometer. Pull the body from the tube to allow the body to hang free. Sling the body around for about 90 seconds. Read the wet and the dry bulb readings from the thermometers on the side of the unit. A key task to understand in conjunction with using a SLING psychrometer is using a psychrometric chart to find relative humidity. From the previous slide and its associated steps, first, take a look at the dry bulb thermometer and record the temperature. This is the actual temperature of the air, not how hot or cold it feels. Next, look at the wet bulb thermometer. Its temperature will be lower than the dry bulb temperature unless it's raining. Record the temperature displayed. Look at the chart. Find the temperature you recorded from the dry bulb on the chart. The dry bulb temperatures are on the horizontal axis or the bottom edge of the chart. Next, find the temperature you recorded from the wet bulb on the chart. The wet bulb temperatures are along the outermost curved edge of the chart. Now, draw a line straight up from the dry bulb temperature and a line straight across from the wet bulb temperature. The point where the two lines intersect is the relative humidity. The next section is on how to use a gauge manifold set. Set the thermostat of the AC unit to a low enough temperature so the unit will run continually during the test. Hang the S hook of the test gauge manifold assembly over the top of the AC unit. Close both the high, which is the red, and the low, which is the blue side, pressure valves on the manifold by turning the knobs clockwise. Next, locate the AC unit's low and high pressure test ports. These will resemble tire valves attached to a tube, with the low pressure port generally on the right side of the AC unit. Verify with the unit's service manual if there is any doubt. Unscrew the valve caps from the test ports. Unscrew the blue low pressure hose from the front of the test gauge's manifold and screw it onto the AC unit's low pressure test port. Unscrew the red high pressure hose from the front of the test gauge's manifold and screw it onto the AC unit's high pressure test port. Open the blue low pressure valve and then the red high pressure valve on the test gauge's manifold, bleeding only the air from the hoses. Close the valves as soon as a refrigerant appears. Take the readings on the gauges and compare to the readings specified in the AC unit's service manual. Unscrew the red high-pressure hose from the AC unit. Open the red high-pressure valve on the test gauge's manifold and then the blue, transferring the pressure from in the high-pressure side of the manifold to the low-pressure side. This will allow the refrigerant to be returned or sucked back into the AC unit. Close the red valve and then the blue. Remove the blue hose from the AC unit. Reinstall the valve caps on the AC unit's test ports. We are now going to review the various components of an air conditioning system. With the exception of absorption chillers, most commercial air conditioning systems are based on the vapor compression cycle. The process can be used to collect heat from air, an air conditioner, or from water, a chiller. It can reject the heat into air, being air-cooled, or water, being water-cooled. The process can even be applied as a heater by moving heat from the cold fluid or outdoor air to a warm fluid, which is indoor air. This is referred to as a heat pump. This slide shows the basic refrigeration circuit using a chiller. It consists of the following four main components. Evaporator. The evaporator is a heat exchanger that removes the building heat from the chilled water, lowering the water temperature in the process. The heat is used to boil the refrigerant, changing it from a liquid to a gas. Compressor. The compressor assembly is made up of a prime mover, typically an electric motor, and a compressor. The compressor raises the pressure and temperature of the refrigerant gas. Condenser. Like the evaporator, the condenser is a heat exchanger. In this case, it removes heat from the refrigerant, causing it to condense from a gas to a liquid. The heat raises the water temperature. The condenser water then carries the heat to the cooling tower, where the heat is rejected to the atmosphere. Expansion device. After the refrigerant condenses to a liquid, it passes through a pressure-reducing device. This can be as simple as an orifice plate or as complicated as an electronic modulating thermal expansion valve. Next, we will discuss the difference between refrigerants. R410A is the HFC refrigerant most original equipment manufacturers have selected to use in new air conditioning units when the HCFC R22 is phased out of all new equipment at the beginning of 2010. This is another step in the overall Montreal Protocol phase-out plan that will ultimately result in the elimination of HCFC refrigerant use altogether. R22 and R410A, while intended for the same type of applications, are indeed very different refrigerants. Therefore, they cannot be mixed, and the equipment they are used in will be different. Neither refrigerant can be used to top off a system that contains the other, and units designed for one refrigerant cannot be charged with the other. Cross-charging can result in poor or no operation, equipment failure, or in some extreme cases, create a safety hazard. This also means that R410A can never be used as a retrofit refrigerant for R22 units. Retrofitting and servicing R22 units require the use of one of the many R22 retrofit refrigerants available. On a very basic practical level, R22 and R410A have three obvious differences: operating conditions, particularly system pressures, lubricating oil requirements, and charging procedures. The main purpose of refrigeration is to move heat from where it is not wanted to where it is wanted. Heat transfer is key to this process. It is possible for a refrigerant to have run-of-the-mill theoretical efficiency, yet be an excellent performer because of its strong heat transfer performance. Good heat transfer allows close approaches in the heat exchangers. This in turn means smaller lifts for the compressor and improved efficiency. Many factors affect heat transfer. Several have to do with the refrigeration system itself, such as piping design and material and flow rates. Three key properties of the refrigerant also affect the overall heat transfer capability of the system. These are viscosity, specific heat, and thermal conductivity. The factors are used in the design of the heat exchangers. The goal is to work with substances that can carry a lot of energy with high specific heats and can transfer the energy easily, high thermal conductivity. It is also desirable to have low viscosity to enhance turbulence and reduce the work required to move the fluid. Ozone depletion potential, or ODP, is an index of a substance's ability to destroy atmospheric ozone. Note that R11 and R12 have the highest potential of 1.0. While the ODP of a refrigerant does not affect its performance as a refrigerant, it is a key parameter. All refrigerants with any ODP either have been or will be phased out as required by the Montreal Protocol. Any new refrigerant or product development must be based on refrigerants with no ODP. Global warming potential, or GWP, is an index of a substance's ability to be a greenhouse gas. The GWP is relative to the warming effect of a similar mass of carbon dioxide for a 100-year time frame. Carbon dioxide is used as the reference gas because it has the greatest net impact on global warming. Halocarbon refrigerants typically have higher GWPs than carbon dioxide, but are in a much smaller quantities. The GWP of a refrigerant does not in itself exclude it from use, but should be considered when evaluating it. Of greater importance is TEWI, or total equivalent warming impact. Next, we will discuss basic troubleshooting of HVAC systems. Before we start looking at common problems related to HVAC, it is important to know the conditions that will exist when the system is working properly. First, the compressor should be running. You can place your hand on it and feel it vibrating. Also, it will feel warm to the touch. The low side of the system should be cool to the touch, particularly from the metering valve going into the evaporator should be cold. Note that although it should be cold, it should not freeze or frost over. Most system evaporators will run around 40 degrees. The high side should be warm ranging to hot. It will be particularly hot from the compressor to the condenser. The temperature should become less hot as it moves through the condenser, but will still be warm until it passes through the metering valve. The fans should be running. If you have gauges and have been trained on how to use them, you could hook up them at this point. Once again, in a system that is working properly, you should see a distinct difference in pressure between the high and low sides of the system. Exact pressures will vary somewhat depending on ambient temperatures and the type of refrigerant in use. Based on temperature-pressure relationship charts, as shown on the screen, normal readings will vary depending on refrigerant type. If we accept 40 degrees Fahrenheit as a desired evaporator temperature, an R22 system normal low side pressure will run around 68 to 70 psi. For R410A, it should be around 115 to 120 psi. As for high side pressures related to R22, you're looking for a pressure that is about 20 degrees Fahrenheit above ambient air that is entering the condenser. So let's say it is 83 degrees outside. 83 plus 20 equals 103. Looking up 103 degrees on the pressure temperature chart for R22, and that corresponds to a 210 psi high pressure side pressure. The same temperature on the R410A chart shows your high side pressure should be about 335 psi. R12 and R134A pressures will generally run around 30 psi on the low side and 200 on the high side. Once again, these will vary depending on ambient temperatures, but you can see that there is quite a variance from one refrigerant to another. Some common problems include plug filters or coils. This will restrict airflow through the coils. On a condenser, this will lead to excessive high side pressures. Unattended, this will lead to rupture of lines and components. When airflow is restricted in an evaporator, this will lead to excessively low side pressures and freezing up of the low side. Unattended, it will freeze up all the way back to the compressor and lead to compressor failure. Freezing up prevents cold air from being delivered to the desired source. Low refrigerant is another problem. If the system is experiencing moderate to severely low system pressures, this will be evident in system pressures. In less extreme cases, a metering device or scale can be used to determine if system pressures are low. Low refrigerant can also be accompanied by irregular cycling of the compressor and fans. Another thing to consider with low refrigerant is the presence of leaks, so leak detection should be done as well. Fans will cycle on and off with the compressor. The symptoms of fan failure are very much the same as plug filters or coils. If condenser fan does not come on, high side pressures will rise. This will put excessive strain on the compressor and reduce the efficiency of the system. Once again, left unattended, this condition will lead to the rupturing of the system and/or compressor failure. Evaporator fan failure will stop airflow through the evaporator and cause it to freeze up. Freezing will continue all the way back to the compressor and could lead to compressor failure. The compressor moves the refrigerant through the system. It takes refrigerant from a low pressure and compresses it into a high pressure. If the compressor fails, flow and compression stop. If the compressor fails electrically, it will not run. There will be no vibration and no noticeable temperature difference in the body of the compressor or the system lines and components. If the compressor fails mechanically, you may still feel vibration from the compressor running, but system temperatures will be the same throughout and system pressures will be equalized. If the metering valve fails, there will be no reduction in temperature to the evaporator and no cold air. If the valve fails in a completely shut position, it will create a restriction. Restrictions will result in the low side being excessively low, sometimes to the point of going into negative pressure or vacuum. Restrictions can also be created by system contamination. A low side restriction will always result in excessively low pressures. High side restrictions will generally lead to excessively high pressures. Contamination is repaired by performing system flushing and relubrication, as well as replacement of filters and possibly the replacement of the metering valve. The next section we will cover is how to troubleshoot and calibrate the pneumatic control system. Pneumatic control systems use air that is provided by an industrial air compressor to ultimately control actuators that in turn control temperature and airflow. Necessary air pressure varies depending on the system. In controlling temperature, air pressure feeds a thermostat. The thermostat controls the amount of air that is sent out to ultimately determine the temperature. How air pressure ultimately impacts temperature can vary. The air from the thermostat could feed a pneumatic actuator, which moves the actuator directly in either a valve or a damper. The position of the valve or damper ultimately determines temperature. Another method is where the air pressure coming from the thermostat feeds an electro-pneumatic switch or transducer. The transducer converts the air signal to an electrical output, which in turn controls an electrical actuator or coil, ultimately controlling temperature. Some of the most common problems related to pneumatic controls include thermostats. It is the device that is most interacted with. As such, it is the most subject to failure. If you are called out on a temperature call, first check the source pressure at the thermostat. Make adjustments as necessary. Verify that output pressure is correct based on the setting of the thermostat. If the thermostat does not operate within parameters, you can attempt to calibrate. If calibration is not possible, replace the thermostat. If there is a break in the line feeding the thermostat, there will be a reduction in air pressure. If the line from the T-stat to the actuator is broken, the actuator will not work properly. A broken line can be determined by jumpering the air lines at the thermostat. disconnecting the line at the actuator, and measuring the air pressure. If the air pressure at the actuator is different than that at the thermostat, then the line is crushed or broken. If the pressure is the same, it will very likely be a bad actuator or linkage. Since the transducer varies power depending on air pressure, verify that air pressure from the thermostat varies as temperature setting changes. Check source voltage to ensure that it is correct. Measure output voltage changes as the thermostat settings change. If voltage does not change as per specifications, then the transducer should be replaced. If the transducer is operating normally, then it is likely going to be a bad actuator or linkage. Next, we will review various ducting and damper systems. Ducts are used in heating, ventilation, and air conditioning to deliver and remove air. These needed airflows include, for example, supply air, return air, and exhaust air. Ducts also deliver most commonly as part of the supply air, ventilation air. As such, air ducts are one method of ensuring acceptable indoor air quality as well as thermal comfort. A duct system is often called ductwork. Traditionally, air ductwork is made of sheet metal, which is installed first and then lagged with insulation as a secondary operation. Ductwork, manufactured from rigid insulation panels, does not need any further insulation. It is installed in a single fix. Lightweight and installation speed are among the features of pre-insulated aluminum ductwork. Also, custom or special shapes of ducts can be easily fabricated in the shop or on site. Flexible ducts, known as flex, have a variety of configurations, but for HVAC applications, they are typically flexible plastic over a metal wire coil to make round, flexible duct. In the United States, the insulation is usually glass wool. A protective layer surrounds the insulation and is usually composed of polyethylene or metallized PET. Flexible duct is very convenient for attaching supply air outlets to the rigid ductwork. However, the pressure loss through flex is higher than for most other types of ducts. As such, designers and installers attempt to keep their installed links or runs short, less than 15 feet or so, and to minimize turns. Kinks in flex must be avoided. Some flexible duct markets prefer to avoid using flexible duct on the return air portions of the HVAC systems. However, a flexible duct can tolerate moderate negative pressures. A damper is a valve or plate that stops or regulates the flow of air inside a duct, VAV box, air handler, or other air handling equipment. A damper may be used to regulate cooling or heating for room-by-room temperature and climate control. Its operation can be manual or automatic. Manual dampers are turned by a handle on the outside of a duct. Automatic dampers are used to regulate airflow constantly and are operated by electric or pneumatic motors, in turn controlled by a thermostat or building automation system. Automatic or motorized dampers may also be controlled by a solenoid and the degree of airflow calibrated, perhaps according to signals from the thermostat going to the actuator of the damper in order to modulate the flow of air-conditioned air in order to effect climate control. Fire dampers are fitted where the ductwork passes through a fire compartment wall or fire curtain as part of a fire control strategy. Fire dampers can be controlled by the fire alarm system. However, in many circumstances, these dampers are held open by means of fusible links. When subjected to heat, these links fracture and allow the damper to close under the influence of the integral closing spring. The links are attached to the damper such that the dampers can be released manually for testing purposes. The damper is provided with an access door in the adjacent ductworks for the purpose of inspection and resetting in the event of a closure. Next, we will go through the types of pneumatic valves and how they operate. Pneumatic valves are one of an array of components responsible for controlling the pressure, rate, and amount of air as it moves through a pneumatic system. Pneumatic systems, which depend on the force of compressed air to transmit power, can be found in countless industrial applications, from pneumatic pressure power tools to diesel engines. Based on other components within a given application and the type of pneumatic system used, one of several types of pneumatic valves may be found at the heart of the device. Functional directional control valves, those that control the direction of airflow or inhibit flow altogether, are a large class of pneumatic valves that houses multiple variants. Many functional directional pneumatic control valves are classified based on the number of entry and exit ports they possess, the number of flow paths they create, and the mechanism by which ports are opened and closed. A two-way directional valve passes air in two directions, through two ports which can be open or closed. A three-way directional valve has three ports, each of which serves a different purpose. The first port is used to connect the valve to an actuator or another device. The second port is connected to an airflow, and the third port is used as an exhaust exit. A four-way directional valve has four distinct ports, two of which connect to actuators, one that connects to a pressurized airflow, and one that serves as an exhaust pathway. They are among the most common types of valves found in pneumatic systems because the four distinct paths allow the valve to effectively reverse the motion of a motor or basic cylinder. This type of pneumatic valve classification refers to the manner in which airflow direction is switched. For example, in a two-way directional valve, the valve is either open, airflow is enabled, or closed, airflow is prevented. In order for each port to assume an open or closed position, an actuator moves a valve spool into position. In two-way directional spring offset valves, there are two positions they can assume when the connected actuator is inactive, open or closed. In devices where an open resting position is standard, air moves freely through the valve. In a closed resting state, the airflow is blocked. In three-way valves, one port is always open. In such cases, a closed resting state usually results in blocking the airflow port, so pressure isn't moving unless the device is turned on. Next, we will review how to calculate airflow. To calculate airflow in cubic feet per minute, or CFM, determine the flow velocity in feet per minute. Then multiply this figure by the duct cross-sectional area, as shown on the equation on the screen. The easiest way to determine flow velocity is to measure the velocity pressure in the duct with a pitot tube assembly connected to a differential pressure sensor. The pitot tube assembly includes a static pressure probe and a total pressure probe. A total pressure probe aligned into the airflow senses the duct velocity pressure and the static pressure, which equals the total pressure. A static pressure probe aligned at a right angle to the airflow senses only the static pressure. The difference between the total pressure reading and the static pressure reading is the velocity pressure. If you connect the total pressure probe to the high port on a differential pressure sensor and the static pressure probe to the low port on the differential pressure sensor, then the sensor's output will be the velocity pressure. After obtaining the flow velocity from the previous procedure, that figure is now multiplied by the duct cross-sectional area to determine the airflow in CFM. There are two different equations for determining the duct cross-sectional area. Both are shown on the screen, one for round ducts and one for square or rectangular ducts. As an example, you can see on the screen, after obtaining the flow velocity and the duct cross-sectional area from the previous two procedures, the airflow in CFM is determined by multiplying the two. Airflow in CFM equals the flow velocity in feet per minute multiplied by the duct cross-sectional area. Building automation systems are often required to measure the actual airflow in air handling systems. Although there are many ways to measure airflow, the two most commonly used with BAS systems are the hot wire anemometer and various devices which measure the velocity pressure of the air. Once the velocity pressure is known, the BAS is then able to calculate airflow. Each method has its own advantages as well as disadvantages. The primary advantage of the hot wire anemometer is that it can provide an analog output that is proportional to flow, and no square root calculation is required to measure airflow. The disadvantages of the hot wire anemometer are that it measures only one point in the cross-section of the duct, and it may require periodic recalibration. Among the flow measuring devices that measure velocity pressure are pitot tubes and averaging tubes. The pitot tube may be used with a differential pressure transmitter to determine airflow at a relatively low cost. However, the BAS controller must be able to calculate the root square of the velocity pressure. Also, the pitot tube measures the velocity at only one point in the duct. Next, we will review how to measure static pressure. It typically should take less than 5 minutes to measure a system's static pressure. Here are sample instructions for a furnace and a remote coil. Step 1. Locate the appropriate places to drill the holes on the supply side, between the furnace and the coil, and on the return side, between the filter and the furnace. Center the holes for neat appearance. Stay away from any coils, cap tubes, condensate pans, or circuit boards to avoid damage. Always look before you drill. Drill test holes using a 3/8 inch drill bit with a metal piercing tip. A bullet tip drill makes a clean round hole. Make sure to use your drill bit sheath to prevent from drilling into the coil. If there's duct liner inside, be sure to penetrate it to assure a good reading. Step 3. Push one end of the tubing onto the static pressure tip. Place the other end of the hose on the high pressure port of the gauge. If required, make sure the gauge is level and zero the gauge by adjusting the screw on the face with the small screwdriver. Digital gauges each zero differently, so check the owner's manual. Step 4. Read the supply or positive static pressure by inserting the static pressure tip in the test hole into the airstream with the tip facing into the airflow. The magnet on the tip will hold it in place while the value is read and recorded. This measurement is the pressure the fan is seeing on the supply side of the system. Step number 5. Read the return or negative static pressure by moving the tube from the high to the low pressure port on the gauge. Insert the static pressure tip in the test hole on the return side with the tip facing the airflow. Read and record the negative static pressure. Don't forget to insert hole plugs in the test holes when you're done testing. Step 6. Calculate the system's total external static pressure by adding the two values. Since the negative and positive signs identify the type of pressure measured, you can ignore them when adding the two values together. An example is provided on the screen for your review. Next, we will go over understanding hydronic systems. Hydronics is the use of water as the heat transfer medium in heating and cooling systems. Some of the oldest and most common examples are steam and hot water radiators. Historically, in large-scale commercial buildings such as high-rise and campus facilities such as hospitals, a hydronic system may include both a chilled and a heated water loop to provide for both heating and air conditioning. Chillers and cooling towers are used separately or together as means to provide water cooling, while boilers heat water. Next, we will review how to read the symbols for HVAC components on blueprints. Shown on the screen are some of the most common blueprint components. For additional, more complicated components to review before the test, an HVAC symbols internet search provides thousands of images. Those in particular that you will want to be familiar with include supply, return, and exhaust diffusers, the various pipes, and the various types of valves. You can follow along with our final section of our heating, ventilation, air conditioning, and refrigeration review inside the MECH Test Preparation Manual. These questions are pulled directly from the manual, and explanations have been provided to help you better understand the concepts being reviewed in the questions. CAT Test Question 1. The pneumatic system is described as A, electronic temperature control interface, B, pressure-sensitive control system, C, control system powered with air, or D, compressor integrated electric system. Answer C is the best answer here because pneumatics is all about using air to control systems. Pneumatics is defined as a section of technology that deals with the study and application of pressurized gas to produce mechanical motion. Answer A is not correct because it relates to electrical and electronic systems. Answer B is not the correct answer because pressure could also include liquids and therefore does not fall in the definition of pneumatics. Answer D is not correct because, like answer A, it is related to electrical systems and not pneumatics specifically. CAT Test Question 2. Pneumatic operated valves respond when controllers A, sense differences in a condition, B, are operated by air, C, operated by static electricity, or D, are tapped with a hammer. Answer A is the best answer here. The key word in this question is controllers. Answers B, C, and D are not correct when focusing on the keyword controllers. Controllers are operated with electricity and then send an output signal to allow the valve to operate, making B incorrect, but they are not operated with static electricity, making answer C also incorrect. Tapping a controller with a hammer is never a good idea, making answer D incorrect, leaving answer A as the best answer here. CAT Test Question 3. Scheduled maintenance means to do all of the following except A, replace an electric motor, B, replace a filter, C, check a cooling tower, D, clean a blower. Scheduled maintenance, also referred to as planned preventive maintenance, or more usually just simple planned maintenance, is any variety of scheduled maintenance to equipment that is a scheduled service visit carried out by a competent and suitable agent to ensure that an item or equipment is operating correctly and to therefore avoid any unscheduled breakdown in time. Therefore, answer A is the best answer here, since electric motors are typically not replaced until they begin to fail. Answers B, C, and D all fall under the definition of scheduled maintenance. CAT Test Question 4. Controllers such as temperature sensors for HVAC systems are A, repaired on site for economic reasons, B, repaired whenever convenient, C, repaired on some devices, or D, replaced when found defective. Answer D is the best answer here. Controllers such as temperature sensors are usually replaced when found defective because of three main reasons. First, controllers such as temperature sensors are relatively inexpensive. Second, controllers such as temperature sensors can have tight calibration bands and often need to be calibrated by the manufacturer. Third and final is that devices these days are becoming more and more complicated, but much easier to simply replace, making the time and effort needed to repair in the field simply not worth it. CAT test question number 5. Valves used in HVAC equipment can be A, repaired in the field, B, repaired only in special circumstances, C, repaired whenever it suits the situation, or D, repaired only with special tools. Answer A is the best answer here and can be determined by process of elimination. Answer B and C is not correct because many HVAC valves can be repaired in many common situations. Answer D is not correct because many repairs can be made with some of the most simplest everyday tools used, such as a screwdriver or a pair of wrenches. CAT test question number 6. Defective gauges are replaced when they A, begin to leak, B, become inaccurate, C, vibrate while taking pressure readings, or D, both A and B. Answer D is the best answer here because defective gauges should be replaced when either answer A or B occurs. Answer C is not correct because gauges may vibrate while taking pressure readings under some conditions, such as rapidly changing pressures, equipment cycling, or defective equipment, such as compressors providing a proper indication of changing conditions. CAT test question number 7. PE switches are A, power to electric connectors, B, P or watts times E, electromagnetic force conversions, C, pneumatic to electronic sensors, or D, pneumatic to electric relays. Answer D is the best answer here because PE switches are pressure electric switches in which a pneumatic pressure change switches the electrical contacts in the pressure switch. Pressure switches can have single contacts or multiple contacts. Note that the design pressure range must match the application, and some have adjustable differential, while others have fixed differential settings. CAT test question number 8. Both pneumatic and electric thermostats can be replaced by A, following the instructions packed with every thermostat, B, memorizing the color codes, C, determining which connection needs to be made first, or D, listening to a coworker's instructions. Answer A is the best answer here because only the manufacturer's instructions will ensure that you replace the thermostat correctly. A couple pointers to always adhere to. 1, purchase a replacement thermostat that will work with your system. Review the compatibilities listed on the packaging of the replacement thermostat. Most replacement thermostats are compatible with all common systems. However, if the system is unique, finding a replacement thermostat may be difficult. Next, review the manufacturer instructions for wiring your replacement thermostat. Most thermostats utilize similar installation methods. However, it's beneficial to read all materials and preview all pictures provided for how to install the new thermostat. Answer B is not correct because depending on the age of the device, the manufacturer of the device, and the previous installer, wire colors may vary slightly. Answer C is not correct because manufacturer's installation instructions may vary slightly from one device to the next. And answer D is not correct because coworkers can have different ranges of experience and knowledge. CAT test question number 9. After a maintenance procedure or repair is completed, the equipment should be A, visually checked before operating, B, manually operated before applying power, C, checked for proper operation, or D, visually checked and then checked under power for proper operation. Answer D is the best answer here because it combines both answers A and C. Answer B is not correct because not every device will be able to be manually operated before applying power. CAT test question number 10. Balancing a system means that A, system components weigh the correct amounts, B, proper flow rates are being supplied, C, return flow is the same as supply flow, D, system components weigh out the correct flow. Answer B is the best answer here. The purpose of testing, adjusting, and specifically balancing in this case is to assure that an HVAC system is providing maximum occupant comfort at the lowest energy cost possible. Answers A and D are incorrect because the use of the word balance has nothing to do with weights. Answer C is not correct because the answer does not take exhaust flow or building pressures into consideration. Comp Test 11, question number 8. When visually inspecting a coil used for heating and or cooling, a person should look for A, dirt, grease, and lint, B, leaks of vapor or liquid, C, deterioration of heat exchanger surfaces, or D, all of the above. Answer D is the best answer here because answers A, B, and C are all correct. When visually inspecting a coil, a person should look for dirt, grease, and lint, but also should be looking for leaks and deterioration of heat exchanger surfaces. Comp Test 12, question number 8. If a heating system is not delivering the proper airflow temperatures, possible causes would be A, dampers closed, B, low temperature water being delivered, C, thermostat not set correctly, D, all of the above. Answer D is the best answer here because answers A, B, and C are all correct. Having dampers closed could decrease the amount of airflow to an area, causing temperatures to be skewed. Low temperature water being delivered to the air handler, fan coil, or other piece of equipment supplying that area could cause temperatures to go out of range by not allowing the equipment to operate properly. And finally, a thermostat set incorrectly may make the system not operate in the desired temperature band. Therefore, answers D is the best answer here. Comp Test 13, question number 8. Read the gauge in the diagram below and choose the correct reading. A, 7, B, 12, C, 17, D, 22. Answer B is the correct answer here. The lines denoted with numbers are the minimum and maximum readings. The maximum reading is divided by the total segments in which the gauge is broken up by. In this example, 50 is divided by 10 to get that each segment is equal to 5. The indicator is showing a reading between the third segment, meaning that the reading must be between 10 and 15. Only answer B has a reading between that range. Therefore, answer B is the best answer here. Comp Test 14, question number 8. Which of the following will help you determine if an air filter should be changed? A, a manometer, B, smoke tester, C, anemometer, D, thermal wheel. Answer A is the best answer here because a manometer can provide readings on both sides of the filter in order to show the pressure drop caused by the filter and any clogging that has occurred. A smoke test refers to a test done on some filters such as HEPA filters to ensure they are properly seated in place, so answer B is incorrect. An anemometer provides the velocity in which the air is traveling through a system, and therefore answer C is incorrect. And answer D is incorrect because a thermal wheel is a type of energy recovery heat exchanger positioned within the supply and exhaust air streams of an air handling system in order to recover the heat energy. Comp Test 15, question number 8. Negative air pressures can always be found in the A, return air duct, B, supply air duct, C, conditioned space, D, hot and cold decks. Answer A is the best answer here. Negative air pressures can always be found in the return air duct because the ducting is located upstream of the air mover or fan and is therefore being sucked toward the fan. Answer B is not correct because supply air ducts are pressurized from being downstream of the air mover or fan. Answer C is not correct because conditioned space can be either negative or positive based on the system balance, and answer D is not correct because hot and cold decks refer to the delivery system for hot and cold air to a space. Comp Test 16, question number 8. An early sign of trouble with the fan can be found in the ductwork assembly as A, smoke and acid fumes, B, slight increase in bearing vibration levels, C, excessive bearing grease, and D, heat discoloration on the scroll housing. Answer B is the best answer here. A slight increase in bearing vibration levels can sometimes indicate an early sign of trouble with the fan. Answer A is not the best answer here because smoke and acid fumes would be more indicative of an electrical problem. Answer C is not correct because excessive bearing grease is a sign of poor maintenance practices. Answer D is not correct because heat discoloration on the scroll housing is usually indicative of late-stage trouble with the bearings. Comp Test 17, question number 8. If a whole wing of the hospital is cold during heating season, the likely cause is A, defective zone thermostat, B, loss of pneumatic air pressure, C, defective zone valve, D, broken circulating pump coupler. Answer D is the best answer here. A broken circulating pump coupler will disable the pump and ultimately the entire flow in the system, causing the entire wing of the hospital to be cold. Both answers A and C are incorrect because of the use of the word zone. Answer B is incorrect because a loss of pneumatic air pressure can result in the system failing in the heat or cold mode and therefore is not specific enough. Comp Test 18, question number 8. If an operating room is hot on the cooling season and the room thermostat indicates 20 pounds per square inch, what would you check? A, air filters, B, delivered air temperature, C, chilled water temperature, D, all of the above. Answer D is the best answer here because it incorporates answers A, B, and C, which are all correct. Answer A is correct because dirty filters could be reducing the amount of airflow being delivered by the system. Answer B is correct because since the room thermostat is calling for cooling, if delivered air temperatures are below desired, the cause may be due to a system cooling failure. Answer C is correct because chilled water temperatures that are higher than normal specifications reduces overall cooling capacity and could be the culprit. This ends the heating, ventilation, air conditioning, and refrigeration portion of CSHI's MECH study guide.